In this video, I'll be going over the 6A section of the semester final review packet. So in this first section, they're talking about whether a model is growth or decay. So if something is growth, that means the B value, we're thinking about this equation now. So the number that's with the X is greater than 1. If it's decay, it's between 0 and 1. So 5/4, although it's a fraction, is growth because it's greater than 1. 1/3 would be decay, and 2 would be growth. Now, if we're going to graph this, I'm going to plot the parent function, which is 1/2 x. Negative 1, 0, 1 are the main points that I need. 1/2 to the negative 1 power is 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. So I'm going to plot these points, but then I'm going to move them all with this transformation here, which tells me I'm moving them all left 2. So I'm going to zoom in. Let's plot these points. So negative 1, 2, 0, 1, negative 1, 1/2. Now I'm going to move them all left 2. So left 2, left 2, left 2. And so my asymptote didn't change since I just moved them left, so my asymptote is still at x equals 0. And then I'm going to have a growth graph that looks like this. All right, the next section is matching. So first I want to think about growth versus decay. So if it's a growth graph, it's going to increase to the right, and that's when my B is greater than 1. If it's a decay graph, it's going to decrease to the right, and that's going to be between 0 and 1. So I can see that this first graph represents growth, and this third graph represents growth, versus the second graph and fourth graph represent decay. Now the other thing I'm looking at is where this asymptote is. So if I notice, I have a +4 asymptote here and here. So that means I'm shifted up 4. And I can see that happening here and here, versus in these two, I have a down 4 shift growth, a down shift of 4, which I can see happening here and here. So then after narrowing it down like that, I can see that I have a growth graph with an upshift is going to be represented with A, and a growth graph with a downshift is going to be represented by D, because both these are going up on the right side. Now, these ones are approaching the asymptote on the right side, so I know these are both decay graphs, B and C. B is shifted up. Oh, sorry, I just realized, sorry about that. This should be, growth is D. Yeah, so this is growth. This is growth. And this is up 4, and this is down 4. All right, sorry. And then decay, this one is decay and up 4, so that represents this equation. And this is decay and down 4, so this represents this equation. All right, on the next page, we're using these equations. So we want to write the equation using 2 points. So that's where this equation is going to come in. Y equals A times B to the X. So remember, 0, 4 is our starting point, meaning my A is 4. And then I'm going to use my other point to plug in for X and Y. And then I'm going to solve for B, because I don't know my rate of growth. So I'm going to put 128 in for Y, 4 in for A, and 5 in for B. So now I want to solve for X. The first thing I'm going to do is divide. Oh, I'm sorry. We are solving for B, and I'm going to put 5 in for X, as I said here. I apologize. Divide by 4. So 128 divided by 4 is 32. So 32 is equal to B to the 5th power. To get rid of a 5th power, I take the 5th root. So my B is going to equal 2. So then my equation will be Y equals my A, which is 4, times my rate of growth, B to the X power. Your formula should always have your y and your x in it because we always need an input and an output. My 4 comes from my A value, which is, I know it's A because my X was 0. And then my rate of growth is what we just solved for. All right, in this equation, they're giving me the model here. A equals 500 times 1.2x plus 125, where time is x in months. Initially, how many rabbits are in the population? So initially would mean when time is 0. So I'm going to plug time is 0 into this equation. And I'm just going to plug that in my calculator. So 625 rabbits. Is the population increasing or decreasing? Now this is going to come from our B value. Remember, if our B is greater than 1, it's growth. If my B is between 0 and 1, it is decreasing. So if I'm looking at my equation, I can see that my B value here is 1.2. So that's how I know that this is a growth or an increasing equation, because my B is equal to 1.2. Now, what percent are they growing by? So I need to figure out, right now this would be 120%. So I need to minus the 1 off, because originally this equation is 1 plus your rate of growth. So my rate of growth is 0.2, or as a percent, I would move this decimal 2 to the right, and I would get 20% is my rate of growth. And then it says after 4 years, how many rabbits will be in the population? So I'm going to plug 4 into my equation, kind of like I did 0 in the beginning, and then plug this in my calculator. And I will get, I'm going to round this to the nearest whole rabbit. So I get 1161.8, so that means 1,162 rabbits. All right, Mrs. Ligmanowski counted 6 tardies in the first week, and then the tardies decreased by 23% each week. Write an equation to model the scenario. So they're decreasing. So this is going to be a decay model, so 1 minus r to the t. So the initial amount I counted was 36, and then they're decreasing by 0.23, which is my percent turned into a decimal, and then the rate of time is t. So that's what this equation would look like. You could simplify it by subtracting what's in here. So 36 times 1 minus 0.23, which would be 0.77 to the t. A new car was purchased for $26,000 in 2010. It lost 14% of its value each year. How much is it worth today in 2023? So now we're going to write a decay equation just like we did above, but we're actually going to solve. So y equals, my initial amount was $26,000 times 1 minus the rate of decay, which is 14%. Again, turned into a decimal. And then t is time. Well, if we started in 2010 and we are ending in 2023, I'm going to subtract those, and we get that my time would be 13 years. So then I'll just plug that in my calculator. And we'll get that the car will be worth $3,659. And since it's money, we should round to 2 decimal places and 77 cents. All right, this last problem is about investments, and it's talking about compound interest. So we have 2 compound interest formulas that were on our other page, but I'll rewrite them up here. The first equation is when we have compounded interest. The second equation is when it's compounded continuously. Something you don't want to write up there, that's okay. So if it's compounded quarterly, that means my n would be 4, and so I'm going to use my PERT equation, not my PERT equation, my A equals P 1 plus R over N T. So my initial investment is $10,000. That's my P. My annual interest rate is my R, but I need to remember to turn that into a decimal. So that'll be 0.042 because we moved that decimal 2 to the left. 15 years is going to be my time. And like we said, my compounded end quarterly will be 4 times in a year, so my end goes into those 2 places. So we're going to have A equals $10,000 times 1 plus 0.042 over 4, and then 4 times 15. Now I'm going to do that 4 times 15. Make sure you put in 60 in the calculator. But I'm going to type this whole thing in the calculator with an exponent on with a 60. So 10,000, 1 plus 0.042 to the 1 plus 0.042 divided by 4 to the 60th power. And we're going to get $18,714 and then 2 decimal places because it's money and 54 cents. Now we're compounded monthly, so we're going to do this very, very similarly. The only difference now is that monthly means my N is 12, but everything else is going to stay the same. So 10,000. So again, the only thing that's going to change is my N here is going to become 12 when it was 4 in the last problem. So over 12, and then 12 times 15. So 12 times 15 is 180, so make sure I put my exponent in at 180. So 10,000 times 1 plus 0.042 divided by 12 to the 180th power. $18,755.46. Now we're compounded continuously, so that's where we're going to use this other formula, PERT. And so my principal, again, is the $10,000. My rate is the 0.042, and my time is the 15. The E is a button in your calculator, so you're just going to use that just as we have been. So $10,000, E to the 0.042 times 15. So again, you want to do this multiplication first, which is 0.63. So when I type in my calculator, I'll do 1,000 times E to the 0.63 power. To find E, you're going to look for your LN button, and so you're going to do your second or your shift and then your LN button. So 10,000 E to the 0.63. And so $18,776.11. All right, the last section before we get into our next video on logarithms, this will be in our next video, is solving exponential equations. Now our goal is we want to get the same base if possible. So my base here is 2, so I can downgrade my base of 8 to be 2 to the 3rd power, because 2 to the 3rd power is the same as 8. So you're always going to downgrade your base, you're never going to upgrade a base. And I want my bases to be the same, because once my bases are the same, then I can solve my equation. So when I have power to a power here, I'm multiplying, so I'm going to end up equaling 2 to the 3x plus 3. Now that my bases are the same, 2 and 2, versus here it was 2 and 8, so they weren't equal there. Now they're equal. Now I'm going to set my exponents equal to each other. So 6x equals 3x plus 3, and then I'll finish solving by moving the 3x over, and I will get x equals 1. Similarly here, I have a 4 and a 16. Well, I know that 16 is the same as 4 to the 2nd power. Distribute the 2. So I'm going to have 4 to the negative 2x plus 10 and 4 to the 2x minus 2. Now that my bases are the same, I'm going to set my exponents equal to each other. So 2x minus 2 equals negative 2x plus 10. Oops, I'm getting ahead of myself. Add 2x to the other side. Add 2 and divide, and we'll get that x is 3.